Yeah, we are seeing your PowerPoint.
Okay, perfect.
You want to try presentation mode?
Yeah, sure. It works?
Yes, so let me introduce you and then we can start.
Okay, perfect.
Okay, so welcome everyone. It is my pleasure to introduce Dr. Riccardo Cucini, a scientist at the Italian National Research Council Institute for Materials in Trieste, where he leads the Sprint Laboratory for High Harmonic Generation and Ultrafast Spectroscopy. Riccardo received his PhD from the University of Florence in 2009, where he developed expertise in time-resolved nonlinear spectroscopy of complex fluids. He then joined the timer group at Electra, where his efforts to push four-wave mixing techniques into the extreme ultraviolet led to a landmark 2015 Nature paper, where he first demonstrated extreme UV four-wave mixing with a free electron laser. His work has been recognized through numerous invited lectures and international conferences, and he holds the Italian National Scientific Qualification for Associate Professor in Experimental Condensed Matter Physics. His current research program spans transient grating spectroscopy, high harmonic generation-based photoemission, and spin dynamics in magnetic materials, which brings us to today's talk, where Riccardo will tell us about all-optical control of Coherent Magnons, a transient grating approach. Riccardo, whenever you're ready.
Thank you very much for the nice introduction and good morning to everybody. Before to start, let me thank Professor Ferguin and Professor Della Torre to give me the possibility to speak at this very interesting seminar series. I look the other videos on your website, so really interesting. So it's a very big pleasure for me to stay here with you and to share my recent research. So let's start. We start with what we would like to introduce you, how it's possible to generate with a special type of four-wave mixing spectroscopy called transient grating, the possibility to control the coherent magnons with an all-optical approach, which is quite new in the world of magnonics or spin waves. So we will speak more or less about magnonics, so what is called the information transport and processing by spin waves. Oh, sorry, I lose. Oh my, okay, sorry. Okay, perfect. So the possibility to information transport and processing by you are able to see my mouse or not?
Yes, we are able to see your point.
Okay, perfect. Okay, so we will speak about in my talk. We will speak about spin waves and magnons more or less in the same way. As you well know, it is not the same things, but for what we want to describe today, we can speak in the same way by spin wave and magnons. So why it's important to speak about magnons? Because magnons allow the implementation of novel wave-based technologies free from the drawback inherent in the current electronics. Let's see some example about this. Oh my God, I lose everything. Okay. So for instance, a very important thing is that if you use a waves instead of electrons, you can work with a vectorial variable instead of a scalar variable. In this way, you can create a wave-based computing, and so you can create non-Boolean computing algorithms that are fundamentals for quantum computing. Another way, in magnonics, you work with the insulator-based spintronics, so you don't need to move electrons, and so in this way you avoid completely the Joule effect. Magnons are characterized by very high frequencies. The frequencies is what is defined your clock rate of computing. So you can increase the maximum clock rate possible for computing. And also you can create nano-sized structural elements because you are not blocked by quantum limitation, like in electrons, where you cannot go towards so small elements. No, you cannot go towards completely nanometers, nano-sized elements. You cannot go down to more than 5 nanometers because the transistor doesn't work. Okay, but with magnon, you don't care about this limitation. From a more general point of view, Magnons are important because are bosons. And like other bosons, they can condensate. But the difference is that you can create a macroscopic quantum phenomena, but not a very low temperature. But in principle, from a theoretical point of view, you can do this at room temperature. And so you can create a condensate of magnon to create a system with low loss information transfer. This is crucial for communication technologies. So what is important is to have the control of magnets. Control means the possibility to generate and detect coherent magnons, and in particular, try to do this with spin wave wavelength very small, smaller than 1 micron, because this is what's important for data processing. What is called generally exchange magnons instead of longitudinal magnons that you have for a dimension longer than 1 micron. And we will see both of them. And finally, the spin wave dispersion is crucial for application technologies, but it's not so easy to measure, we will see why. So, at the first step, I would like to introduce you the possibility to create a magnon, but following the phonon-magnon coupling. What does it mean? Well, it's possible to create a connection between surface acoustic waves and spin waves due to the magnetostriction. Magnetostriction is an effect that can be direct or inverse, with which you can change the magnetization and in this way generate spin waves, surface acoustic waves, or use surface acoustic waves to generate magnetization. This is our channel. Why it's important? Because as you well know, if you have a magnetic system in an external magnetic field, the dynamics of your system is following by this very famous formula, the Ginzburg-Landau formula. And what is happening? You start a precession, so a motion of the spin around the external magnetic field, but unfortunately, at a certain point, when the two magnetic fields are parallel, all the dynamics is stopped. So it is not so useful. If you want to use this, you need to maintain this movement, removing the Gilbert damping, because if not, you cannot use in a device. So a possible way to do this is to compensate the Gilbert damping with an external field and create a resonances in order to stop this damping or to control this damping. This is mainly due by radio frequencies. What is happening is that at a certain point, you can compensate the two things, the two movements, and so you have an oscillation or a spin wave that maintained without damping. So there are several possibilities to do this with radio frequencies or electromagnetic wave in general. We will try to do this with surface acoustic waves. Why? Because surface acoustic waves mainly are characterized by dispersion, which means that the frequencies is as a function of the induced wave vector. In some experiment, you are not able to change your wave vector. In our experiment, we can do in a small range, but in principle, it is not so easy. So when you have a surface acoustic wave with a fixed wave vector, you can couple with spin waves more or less ever. But if the coupling is not so strong, the only possibility to enhance the generation of a spin waves of a spin wave pumped by surface acoustic waves is to find a resonances, as we saw before. But if you are, for instance, here, where is the red point in your experiment, your spin waves, the dispersion of this spin wave is this one, you have no crossing. So how it's possible to create resonance? To change the wave vector of a surface acoustic wave is not so easy task. But what is easy is to change the dispersion of spin waves by simply changing the external magnetic field. So if you tune the external magnetic field at a certain point, you can, in principle, overlap the wave vector of your surface acoustic wave, creating resonance. This is in principle. Let's see if it is possible. For instance, what we try to do, we try to generate with an all-optical approach a surface acoustic wave with a fixed wave vector, with a not zero with vector, and implement a magnetic sensitivity in order to be sure that we are able to generate a surface acoustic wave, but also that we are able to couple the surface acoustic waves with the spin waves. It can be done with a well-known experiment which is called Transient Grating. I don't know if you are confident, so let me spend very few words on the experimental setup. In a transient grating experiment, two high-power pulse lasers interfere inside the sample, producing a spatial modulation of the index of refraction. This modulation can launch two counterpropagating waves whose superposition creates standing waves. The standing wave oscillates with a velocity, which is the velocity of the sound inside the material. This beam can be, dynamics can be probed by a third beam that impinges on the sample and is diffracted by it. And a measurement of intensity versus time of the diffracted beam give you information on the relaxation of the grating and so on the relaxation of the whole excited mode. Peculiarities of this technique is the so-called phase matching. Phase matching means that if you have a thick sample, thick means a thickness larger than the pitch of the grating, what is happening is that all the energies of the probe is diffracting in a very fixed angle, creating a completely background-free technique which allows to follow very small signal. The wave vector, so the wave vector induced in the sample, so the phase matching condition fix the wave vector inside your sample that depends only by geometrical condition, which means the angle between the pump and the wavelength of the pump. So you can tune your wave vector by simply changing the angle or changing the wavelength of the pump. What are the possible field matter interaction? The first one, also the smaller one, is what is called the electrostriction. Electrostriction means that you have a migration of the induced dipole towards the region with the higher energies. In this way, you can generate a density grating that changes your dielectric constant or your index of refraction, and so you can create a real grating inside your sample. Another possibility is to have absorption of the radiation. And so in this case, you have a migration far from the region of a highest of a constructing interference. And so you create a temperature grating and again a density grating. In this way, again, you can change the dielectric constant. Another possibility is that we will not speak here in my talk is the electric torque. If you have molecule that can be torqued with the electromagnetic field, you can create an orientational grating and then possibility also a density grating and again a variation of the electric constant. So you can measure all the dynamics related to the density, to the temperature, or to the orientation. So these are few historical application of transient grating. The first one is probably the most powerful on the liquids or confined liquids, where you can really gain for the high signal to noise ratio you have in your system, but also from photocarrier dynamics, so something that works at faster time. If you have, for instance, very short pulses around 45, 50 femtoseconds, you can also follow the photocarrier dynamics. You can have something in the middle or longer time for hundreds of nanoseconds or also microseconds. If you look at the thermal diffusion due to the complete relaxation of the thermal grating, you can have the surface acoustic waves, which is something that we will see here. It is quite recent. And finally, but not finally, also the spin dynamics, in particular due to the relaxation of a spin gratings or a concentration gratings, and so you can follow also the dynamics of induced spin. This is just few possible experiments, but you can find in literature a very large possible application of transient grating. which is again not so diffuse technique, but can cover a very broad types of physics. So this is a standard experimental setup, is the one that we have in our lab. As you can see, what we use is an ytterbium-based laser at 130 nanometers. We split in two here, and we have the pump and the probe. The probe is doubled in frequencies. It can be also changed with a continuum wave laser, so you can study the fast dynamics and the long dynamics by simply changing a mirror. And then they are overlapped on the phase mask, which allow to create, as diffraction order, the two pumps and the probe. You have a lot of diffraction, but you can stop all the beams, and you can use only the plus and minus one for the pump and the plus one for the probe. And then the phase matching conditions, so the condition at which the conservation of energies, the conservation of momentum is established. And so you have the diffraction only in one direction for a background phase signal is completely defined by the geometry of the phase mask. So you don't need to do nothing. You simply have to collimate the beams and focalize again in the sample. So it's a very easy way to create a transient grating setup. And then you can work in transmission in this case, or in reflection, check the diffraction in reflection for not transparent beams. And you can acquire them with the photodiode and the lock-in amplifier. When you use the continuous wave probe, you can also again make the same experiment, but what is useful, you can implement also the so-called heterodyne detection. Also with the pulsed probe you can do, obviously, but with the continuous wave probe, it's particularly easy to do. In this way, you can increase. It's a smart way to increase the signal-to-noise ratio of several orders of magnitude, which is really important if you have to see very, very small signals. Finally, what you can do, you can also stop the probe. Don't care about the probe with the transient grating. You can create the grating on the sample, but you can probe with a single beam that can be reflected. No diffraction here, but simply reflection. And if you look at the reflection, or eventually at the transmission, if you want, you have something that can control your polarization. You can create a transient grating pumping and the time result polarimetry. So in particular, you can look at any possible dynamics related to the variation of the polarization of the probe. And we will see several applications on it. So let's start with the transient grating standard. This is our parameter. And this is the range of the wave vector fixed by our phase mask. By following this, we fix the angles. So this is what we can obtain. Now we can enlarge a bit this range with the new mask, but more or less you tend to stay between 1 and 10 micrometers at -1, typical. Then what you can do, when you have generated this, if you put your magnetic material inside an external magnetic field, if you look at the rotation or the polarization, you can make what is called time result Faraday polarimetry, or Kerr polarimetry if you work in reflection. And thanks to this, you can follow only the dynamics related to the spin waves if you are able to generate. So in this way, you characterize from a surface acoustic wave point of view, with this from a spin wave point of view, by separating completely the two contributions. This is a very important aspect of this approach. So let's start with the acoustic signal. We know that we are able to do this. We have a few nanometer thickness nickel on a glass substrate. This is what you saw if you measure with pulsed probe the system. If you make the Fourier transform of the signal, you can observe that you are able to excite two surface acoustic waves. In our case, we have the so-called Rayleigh surface acoustic waves and the surface skimming longitudinal wave. These are only two possible waves in any, depending by the sample, you can have a large amount of possible waves that you can generate, but this is what happened in our system. So we are sure that we have a surface acoustic wave. It is possible to couple this with a spin wave. This is the original question. What we do, we use the other approach, so we look only to the rotation of the polarization, and we observe that at two different external magnetic fields, we found two different signals. The only two signals possible that are able to see at these two frequencies. Far from this, you don't see nothing. If you make the Fourier transform of this, what we saw is that the frequencies is exactly the same of the surface acoustic waves. So we have reached at these two values of the external magnetic field a resonance of the resonance at the same frequencies. So in other words, our surface acoustic wave is able at these two magnetic fields to pump a spin wave. So in other words, you have a phonon pumped magnons upon tuning the external magnetic field. And this is the peculiarity, because your spin waves have the same wave vector of the surface acoustic waves. So you generate a coherent magnon with a non-null wave vector. And this is this is a very important peculiarity that you cannot obtain with other techniques. This is all you have in this picture, the time delay across on the vertical direction, the applied magnetic field. As you can see here at 0, you don't see nothing. Then if you increase the bit, you see in a small range for oscillation and then more oscillation. If you make the Fourier transform for positive and negative magnetic field, you plot these, the frequencies of your spin waves with respect to the magnetic field. This plot is called ferromagnetic resonances. It means that if you change the wave vector, you change the frequency of the surface acoustic waves. So you can put here, you can put here several points, and you can rebuild completely the ferromagnetic resonance, but with the all-optical approach, and with a wave vector different to 0. You can also extract also not only qualitative information, but also a quantitative information. In particular, if you use the standard formulas coming from the ferromagnetic resonance, you can extract from the measured frequencies the effective magnetization of your system, and you can also measure by the bandwidth, the Fourier maximum of this dimension. You can also measure what is called the inhomogeneous broadening, which is related to the quality of your sample. If you try to do this with several wave vectors, you compare with the standard ferromagnetic resonance, here is the range where they are overlapping, what you observe is that our value for the effective magnetization and the one obtained with standard ferromagnetic resonance is exactly the same. What is strange in principle is that the inhomogeneous broadening is not exactly the same. Why? The sample is the same. So if you don't have, if a sample has several inhomogeneities, it's for both of them. But this is the key, because the ferromagnetic resonance is area integrated technique. In our case, we are able to measure only in the spot of the laser, which is around 40 micron. So we saw a smaller inhomogeneity because we are looking only in a small point. This can have two consequences. The first is that you don't care about eventual inhomogeneities of your sample because you can overcome this. Or if you want, you can map the inhomogeneities of your sample by scanning the point, your sample across the focal spot of the laser. So two other possible applications apart from the phonon pumped magnons. So in conclusion, in this part, we saw that it's possible to generate surface acoustic waves and to probe simultaneously the acoustic and magnetic dynamics by completely distinguish the two contributions. This is a complete contactless technique, so you don't need for lithography. What you do when you study surface acoustic wave, you put some transducers on your sample, but in this way, you cannot change the wave vector, and you have to change the sample every time you destroy your sample. Okay? You can change easily the wave vector. We demonstrated it's possible to have a phonon pumped magnon with a non-null wave vector. And the comparison with the ferromagnetic resonance from a qualitative and quantitative point of view are both good. So let's start to have a step forward, a new way to make time-resolved polarimetry in a very special sample, which is called a magnonic phononic crystal. What is a magnonic phononic crystal? It's a material on which you may create a periodic modulation of the magnetostatic and the elastic properties by simply changing the surface. For instance, you can create an array of magnetic nanowires, which is the one we will use in our experiment, or you can create a very fancy geometries, which are the milled antidotes in a continuous field, or you can also change the properties at the surface, like in this case, you can modulate the surface properties, and you can create what is called the Diallo-Chisky-Moria interaction, which is really important for another very fancy quasi-particle, which is the skyrmions, that recently in the last year are becoming very, very interesting for the magnetic communities. What is important, and why are important on magnonic phononic crystal? Because you can create artificial pseudo-brilliant zone, and so you can create forbidden and flat mode, forbidden bands for the surface, for the phonons, or for the magnon. And you can tune this band gap, so you can change completely your material by simply changing the periodicity of the nanowires, the thickness, the materials, and so on. And this is important because the contour of these magnetic properties are very important for a lot of system or material that are used in magnetics. So we try to use this type of magnonic phononic crystal using iron and permalloy with this very short separation between the strips, but with a very large strip. And what we try to do is something that is similar in such a way to the transient grating, because in this case we use only one pump, but the pump illuminates several strips. So with one pump you can obtain something similar of what you obtain with the transient grating. And then we probe with the magneto-optical Kerr effect, because in this case it is not transparent. What does it mean similar to transient grating? Well, if you use, for instance, silicon, and you have this, you put your beam here, you have a strong pump absorption on the nanowires. In this case, the heating passed through the silicon substrate, and so you have a standing heating patterns that became a strain pattern, because you can launch here again surface acoustic waves. So, or you use two pumps and interfere in it, or use one single pump, and thanks to obviously the shape of your sample, you can generate again surface acoustic waves with a wave vector that is fixed by the distance of the nanowires. So it's a different way, more complicated, but a different way to do this. And what's happening here? Well, just to be sure that we are really able to generate surface acoustic waves, we use again the same setup of the magneto-optical Kerr effect, but we don't check for the rotation of the polarization, but we are looking only at the polarization that have the same versus of the polarization of the probe, not crossed. In this way, we saw two oscillations that give us the generation of two elastic peak around 9 and 11 gigahertz, that can be associated again to a pseudo-Rayleigh surface acoustic waves. And the other one is a localized breathing mode inside the strip, so the vibration of the single strip. And you can compare this value with the electric charge that is good. So in this way, you are really generating a phononic mode. But if you look at the standard magneto-optical Kerr effect, what you saw is that you are able to see a pure magnetic signal here in the blue line. You see something, a signal that depends by the external magnetic field and the angle between the external magnetic field and the line, typical of a magnetic properties. What's happening? Well, if you hit your strip, you have a change of the magnetic field, and also you change also the magnetic anisotropy. So you have a new axis around which it starts to have a precession until it is became again parallel to the external magnetic field. So this type of precession is exactly a spin waves, but the spin waves here is fixed by the single strip, so a spin wave inside the strip. Just to be sure that it's true, we compare our results with the Brillouin light scattering and also simulation that give us more or less the same results. So we can assign this magnonic mode to a uniform precession in each nanowires. So look at the wall signal. What you saw is something like this. If you measure again the frequencies with respect to the magnetic field, you see two lines and a tiered strange signal. What does it mean? We call Mach1 and Mach2, which means magneto-elastic coupling, because this is exactly what we saw before, because the spin wave coupled with the surface acoustic waves, coupled with the spin waves, like happened in the previous experiment. But here, the magnetostriction is very strong, so you don't need to go to the resonance because it is every time present. It doesn't depend by external magnetic field because it is pumped by the phonons, but appear only in the crossed polarized section. So this is for sure a magnetic signal, but due to the surface acoustic waves. Something similar to what we had before. But you have also a pure magnetic mode here that is due only to the spin wave inside the single strip. So if you try to fit at the fixed external magnetic field, you have here three modes. This is the complex signal. If you want to remove this signal, which is a little bit far, you observe that here you can fit exactly this point where you have a crossing between the pure magnetic mode and the magneto-elastic mode. What's happening there? When you have the cross, it seems that they sum together by looking at this. But this is a pitfall, because if you look at what you can extract from the fitting of the signal, you can observe that you have what is called an hybridization gap. It means that what is working like a phonon start to work like a magnon. What is working like a magnon start to work like a phonon. This means that the frequency that you expect to have here, so this point where you have uncoupled mode, is not present. So this is not a cross, but this is an avoided crossing. This is what is called in magnetic the opening of the von Neumann-Wigner hybridization gap. This is really important because it's quite famous as a coupling between photon and magnon, but it's the first time that is demonstrated between phonon and magnon. So the von Neumann-Wigner theorem can be applied here, can be demonstrated also for phonons and not only for photons. But there is something strange, because what you expect when you have the hybridization gap here, it corresponds to a crossing between the two damping, but at the same point, the same magnetic field. It doesn't happen. Why? It's strange. So in order to understand better this mismatch, we need to dive into an Hamiltonian modeling of the coupling, but a very, very simple model. We are experimentalists, we are not theoreticians. So something very, very simple. This is what we have here. We simply use a terms for the magnons, a terms for the phonon, and the terms that consider the coupling where we fix a strength G and the phase phi. What's happening if you plot this? Well, if you take phi equal to 0, what you have is what is called coherent coupling, where you have an energy repulsion and a damping crossing, but exactly at the same frequencies. Here we consider the uncoupled mode tuning, so we use 0, the point at which we had the crossing. On the other side, if you go to phi equal to pi, you have what is called a dissipative coupling, which is due to the energy attraction and a damping repulsion, but this is not similar to what we have again. But again, this behavior happen at the same frequencies. What is happening if you go to in the middle, you have exactly what we saw. So you have a mixed coupling, which is characterized by the symmetries, where here you have the energy repulsion and the damping crossing happen at two different external frequencies. So let's try to see in our case what's happened. If we try to fix this at 60 degrees, which is the angle between the external magnetic field and the strip, what we saw, if we fit the data with our simple formula, we saw that we have a weak mixed coupling. Weak with respect to the uncoupled mode. So you are generating a mixed coupling. So it's possible to play with this. Well, if you move not in plane, but out of plane, the magnetic field for a small angle, for instance, 15 degrees, what you saw that now you have again the standard condition for coherent coupling. So this is really important because by simply changing the magnetic field, the orientation, you have a magnetic knob with which you can change the type of coupling, and so the type of functionalities that your potential magnetic system have, and you can tune by simply changing the angle. So you have a system and its behavior can be completely changed by simply turning the direction of external magnetic field. This is exactly what you want from a technological point of view. So let me conclude also in this part. We show a magnetic crystal is an ideal platform for magneto-elastic coupling. We observe for the first time the mixed magnon-phonon coupling, and we expect that you can extend the type of approach also any other possible quasi-particle. Probably we found a knob to tune this coupling mechanism. And obviously, the next step is try to use new geometries with new material to improve the strength of this coupling and see what's happening. And also try to consider the frequency damping mismatch as an experimental identifier of the coupling between any possible quasi-particle. So as a starting point for a possible to opening the way to study different coupling between different quasi-particles. I want to conclude with the final step, which is the way to again generate coherent magnon, but with a direct way, not with non-phonon pumped or pumped by magnonic crystal, but a direct excitation of coherent magnons, again with transient grating spectroscopy. So what we use again the Van Kampen approach, which is what I echoed before. With when you illuminate with the pump system, you have a strong demagnetization. So you have a new equilibrium magnetic field. So starting from this point, you have the precession around this for this oscillation, and then in the end you have a different position because you have again the magnetization. It will relax at a very long time to the previous point. But this is at null wave vector because it was done by a single pump. If you do this with a transient grating, you have again the same effect, but you have this effect only in the hot stripe, where you have a constructive interference. Why here you don't have it? So here you have precession, here and here, but here not. So you have again a precession like in Van Kampen experiment, but here the wave vector is not null because it is given by the transient grating wave vector. So a way to generate a coherent that directly by simply by hitting the sample. This is due to the fact that when you hit the sample, you have a Curie temperature that can be passed through you can pass through the Curie temperature, but also if you don't pass through the Curie temperature, you simply hit a bit, it's enough to change the anisotropy. Okay, so you can every time, if the sample is good, to generate this type of spin waves. But the wave vector is fixed. So we try to test this with the standard transient grating, so with the cobalt-gadolinium gadolinium alloy. And what we did, we tried to use a system which is characterized by the perpendicular magnetic anisotropy. So if you stay at 90 degrees, where the external magnetic field and the anisotropy is parallel, they are already parallel, so no way to have a precession of the spins. You don't see nothing. You see simply the relaxation of simply the demagnetization. But if you change the angle, what is happening? You see an oscillation that appears. This oscillation is looking in vertical horizontal conditions. So it means that your probe is vertical, but you detect horizontal, which is what you need. You look at the variation of the polarization of the beam, which is sensible only to the magnetic case. If you try to change the intensity of the external magnetic field at a fixed angle, you see that you generate different frequencies for different magnetic field. But they may be also acoustic oscillation, so phonon pumped again, or not. Well, to do this, you simply put the detection in vertical, and what you see is that you see a very beautiful surface acoustic wave, the same we saw before, but the frequencies are different. This small part, for sure, is given to phonon minor coupling, but not this. So these two frequencies are pure magnetic, so are pure spin waves, not phonon pumped spin waves. If you just to compare with the literature, we want to compare if this corresponds to the standard ferromagnetic resonance, and we saw exactly the same. So more or less, we have a wave vector different to zero, but the signal corresponds to a ferromagnetic region which is characterized by zero wave vector. So changing the wave vector doesn't change nothing. Yes, in this case, because we are using very small wave vector. So here we are, the magnons that we are able to see is longitudinal magnon, so very long wavelength magnon. In this case, the dispersion is almost flat. So zero wave vector or not zero wave vector doesn't change nothing here. But it demonstrates that it's possible to generate spin waves with a fixed wave vector directly. So now, if you know this, you can move forward. If you remember here, my first slide, what I saw is that you want to measure for the data processing the exchange magnons, not the longitudinal magnons. So you want to go with a wavelength smaller than 1 micron. With the transient grating, we are around micron, a few microns. So it's possible to use the same technique, but to push forward the limits and to go to see what's happened with exchange magnons. Well, if you remember what is transient grating, if you want to change the wave vector, you can change only the angle, but the range that you can cover is small, but you can change completely the wavelength. In fact, if you go toward the extreme ultraviolet regime, you can do a transient grating, you can create a nano gratings. But how you can do this? Because you don't have lasers in this range. Lasers, no, not tabletop laser, but you have free electron lasers. In particular, the one that we have here in Trieste, that is called Fermi, it's able to do exactly the same, but with the wave vector, which is more or less 2 orders of magnitude larger with respect to what we have in the tabletop laser type. And here the wavelength, the pitch of the transient grating is around tens of nanometers. So now you are exactly in the right range. Here we use iron gadolinium instead of cobaltum gadolinium because we want to be sure to have a strong signal. So just to see if it works, which simply changed the sample. And we did exactly the same experiment on the timer beamline, where you have exactly the same configuration. And what we measured? Well, we was able to see a signal, again here an oscillating signal, but in this case you are not able to observe a polarization orthogonal to the probe. So how you can be sure that it is a real coherent nanomagnons? Well, just to understand this, we use two different samples. The one will be called CMA, which means compensated magnetic anisotropy, and the second one, PMA, the perpendicular magnetic anisotropy. Here means that the magnetization on the surface of the material is completely compensated by the perpendicular anisotropy. So here, when you are a external magnetic field parallel to the surface of the sample, you have your spin all oriented on the same direction of the external magnetic field, and you don't have precession. In fact, if you go at theta equal to 0, you don't see any signal that appear if you change the external magnetic field. What does it mean? That here the signal is for sure magnetic because it depends by the angle. And when you go at the angle where you don't expect magnetic signal, you don't see nothing. If should be a phonon pumped magnon here, you expect to see oscillation also for theta equal to 0. But it is not true. So you are sure that this signal is pure magnetic. If you do the same with the other one, you cannot reach the same condition here because perpendicular means that your magnets have to stay perpendicular to the surface. But if you do this, and you rotate this in this direction, you completely stop the beams. So you cannot do this, but what you can try to do is switch off the magnetic field. And as you can see, if you switch off the magnetic field, remain only the ultra-fast demagnetization, but no precession is given. So you are sure again in this case that you have a pure coherent magnons. So a step forward is try to see what's happening if you change the wave vector, because we saw that the longitudinal magnon had flattened dispersion, but not the exchange magnon. So we make the experiment at different wave vector for the two samples, and we plot the frequencies with respect to the wave vector, which is a standard way to plot the dispersion. And as you can see, these have exactly a dispersion, and in particular, it depends by the square of the induced wave vector, which is exactly what you expect in the case of exchange magnon. So this is the first experimental demonstration that the exchange magnon can be detected, can be excited and detected in the extreme ultraviolet range. This is the first demonstration. So, in conclusion, the transient grating technique, this is the take-home message, can be used to excite spin wave and selective wave vector in several different ways, okay? Direct or indirect way. And it's possible to extend in the extreme ultraviolet range to make the first evidence of the exchange magnons, and not only longitudinal magnon, and measure for the first time the dispersion, which is really important for the application on devices. So let me thank all my collaborators, in particular the people from NFFA Sprint lab, and all the people from the Fermi building, for the Fermi free electron laser for the extreme ultraviolet measurement, people from the synchrotron creating the samples, and also people from University of California and Massachusetts Institute of Technologies to create together the experiment with the free electron laser and also with the tabletop laser. And this is our lab. Our lab is a lab inside this European and now Italian facilities that can be accessed directly for external user. So you can apply to have a completely reimbursed beam time, you can access to several techniques like the transient grating. We have a lot of laser sources. In the future, we will have also we have now ready but not yet open to use it time-resolved Raman and time-resolved photoluminescence, and also the generation of high harmonic sources, generation sources with which we can make time-resolved and spin-resolved photoemission on magnetic surfaces. And if you are interested, you are welcome to visit our lab. In particular, we have several possibilities to have a postdoc position. So if someone for you is searching for a postdoc position, please let me know. And thank you all for your attention.
Thank you, Riccardo. This was very, very interesting.
I hope I was in time, or
you're perfect.
Okay, good.
Let me. Are there any questions in the audience before I ask?
Yeah, sure.
You can either raise your hand or unmute yourself. If not, I would like to. So I have one question about the second topic.
Okay.
Regarding the coupling between the magnons and the phonons.
Okay. Now let me.
And I think I might have missed this. Yeah. Yes, okay. I think if you go 2 slides more, like slide 23. 24, slide 24, sorry.
Here?
So, yeah. I think I missed, what do the red and the blue curves correspond to?
Sorry. This red curve here corresponds to the fit of this data at a fixed magnetic field where you have the Mach1, the Mach2, and the pure magnetic mode. Because if you cut here, you have 3 modes. Then for simplicity, we remove this mode because it's quite far, just to see that when you cross the beam, you can see really easy both of the signal. Okay.
And then I have another question about the comparison with the fit to the data with the crossing, like the damping and the energy of the modes. I think it was like.
Sorry.
Actually, the theory works. And this is something that I found, like slide 25 works as well. And this is something that I found counterintuitive.
This one?
Yeah, this one works.
Okay.
For the weak coupling.
Yep.
And maybe this is just a coincidence, but it seems that the avoided crossings and the change on the damping when one mode is more damped than the other happen at different fields. So at the avoiding crossing, they have comparable damping, but then it takes a while for the damping to flip. But for the coherent coupling, it happens at the same time.
Yes, more or less the time is not is more or less the same. It's not exactly the same, but it's more or less the same. Yes, from a theoretical point of view, I have no explanation for this, but because we simply extract this information about our simple expect. I'm not completely sure that you expect a difference in the damping.
Right.
Okay, it's not necessary that to be so different. Okay.
Right. Okay.
No, you don't need, because the interaction is different, but both the coupling, in this case, is a weak coupling. Okay, so the interaction is not so strong. So what gives mainly the quantity of that relax completely is the fact that the part of coherent coupling is dominating. So the dissipative coupling is small in intensity, and so doesn't affect so much the two relaxation.
I see.
Which is the main difference, is that here, with respect to here, you have a little bit more dissipation. But the dissipation it can be really different in terms of time, but here is very small in terms of amplitude.
I see.
So affect not so much the final results.
I see. I have one more general question.
Okay.
Sure. You do these both in ferromagnets and antiferromagnets? Like the
Never in ferromagnets. We never tried in antiferromagnets.
Have you tried
No.
altermagnets?
Sorry?
Have you tried altermagnets?
No. We work with altermagnets in our group, in particular in synchrotron. But when we did this measurement, we prefer to work with something that will work. Cobalt, iron, you are sure.
Right.
Not sure, then let's see. But yes, altermagnets, it's a part of research that we perform in our group, which is a very large group. People also work in synchrotron, in particular with spin resolve photoemission, and they work a lot on altermagnets. So it may be a next step for us.
Okay, and is it possible to go to low temperature, or like is it too hard to integrate a cryostat?
No, with the transient grating, we can go. We have an cryostat that we can go no more than 40, 45 Kelvin.
Okay.
No lower. Okay. Because we use an anti-vibrational cryostat, so we have very small space.
Oh, I remember. Yes.
And we don't want something that vibrates a lot.
Right. Cool. Any other questions from the audience?
Can I ask a quick question about this slide? You mentioned improving the coupling strength. So do you have any strategy to reach the strong coupling regime between the phonons and magnons?
Well, the only knob we found, but there may be more, it's only the variation of the angle between the external magnetic field and the strip. The problem is that the variation is small, only 15 degrees, because if you go for more, you stop the beams. Okay, so in principle, you can create a different type of magnetic field by going to the back of the sample, so going directly at 90 degrees and see what's happened. But we never do. The other way to understand this is try to change materials. Okay, so try to change, but also simply the shape of the strips of the nanowires. But we have not done this. No, not yet.
So the shape of the magnetic materials will change. Would that change the dispersion, or?
I really don't know if what maybe simply because it's the simple way to change something on your sample, no? Because for instance, the only things what I've learned in my career that if you want to do something in the magnetic world, you have to change the temperature and to change the magnetic field. You have no other things to do. So this is the most simple things, but for sure the shape may be really important because the shape change completely the magnetic behavior.
Okay, thank you.
I have a question about the setup, actually, like the more general setup that you presented at the beginning.
Sorry.
Could you, instead of using the green light, could you use like some wavelength from the OPA, or do you have to be a harmonic to get the right diffraction from the transient grating?
Okay, from this setup, you cannot change the wavelength of the probe because the achromatic doublet are giant, are 3 each. They are optimized only for these 2 wavelengths, which is crucial if you want to have a correct overlap on the sample. So with this setup, you cannot do. Currently, we have not yet done, but we have several OPAs. So in principle, we can go inside the setup, but you have again the same problem. In principle, you have to change this part and to use mirror to make a broadband setup, so you can work with mirrors instead of achromatic doublets. You can do. We tried to do this in the past. It was a starting point, but it's not so easy to manage because they are very, very big. You have to work with off-axis parabolic mirror that are a nightmare to align.
Right.
You have not enough space to put your finger inside. So if you have enough space, you can do. But if this is very compact, with the mirror became more compact,
Right.
so it's not. But absolutely, it's possible. Yes.
Okay, I see. I see. Cool. Yeah, I think if there are no further questions, let's thank Riccardo again for a great talk. This was very, very interesting, Riccardo. Thank you.
Thank you, all of you, for inviting me. It was a very, very big pleasure. And I'm very interested to all the other seminar you do. So thank you very much to invite me. I'm very happy for this. Thank you very much.
Hopefully we see each other in Trieste at some point.
If you want, you're welcome. Absolutely, yes.
Yeah. Thank you so much.
Okay.
Yeah.
So,
No.
you will come in 19, you are in Roma, you will move also around Italy. If in any case you have a trip also for holiday in Trieste, let me know and we can.
Yeah, I'd love to go. I'd love to go, but this is the end of my stay. Unfortunately, I'm leaving in a week.
Okay.
I was here for 3 months.
We have also beautiful sea, better than in Rome.
In your
I
way
know.
to
I've been to Trieste. I've been to Trieste.
Sure.
I know.
Cool.
Okay, thank you very much.
Thank you.
Thank you, Riccardo. Bye-bye.
Bye-bye.